Electrons represented with arrows, finding homes in little boxes, which are orbitals, placed at subshells, principal energy levels, all that. So broadly speaking, when we come up with what's called an electron configuration, we're coming up with how the electrons are configured or hanging out associated with an atom. We're going to focus on electrons as if that set of electrons are all hanging out in their ground state. So like as I do this, I'm kind of going as close to the nucleus as possible. It's going to be the lowest energy as possible. Did you guys hear that? Okay. So just to make sure we're all on the same page, so here's the periodic table. So if I circle boron right here, okay, how many electrons are on a neutral boron atom? Hands, please. 5. There are 5. Yep, it's atomic number 5, so it's 5 protons, and if it's neutral, it has 5 electrons. Exactly. How many electrons around? Oh, you don't have to use your hands, but how about xenon atom? 54 electrons. Yep, that's true. 54 electrons. So we need to see how those 5 electrons are hanging out in their ground state around a boron atom, or those 54 electrons are hanging out around a neutral xenon atom. Now I'll tell you, this gets a little cumbersome. 54 electrons, that's a lot to find homes for. This one's easier. This one makes me smile. We'll have an assortment of both, okay? So to find homes for those electrons, we are going to ultimately use what's called the lowest n plus L rule. To kind of remind you how that works, of course, n is the principal energy level. N is equal to 1, is 2, 3, 4, all the way up to infinity. And remember the L value is, so this is orbital type. This is probably what you guys covered in maybe high school chemistry. And now this is the L value. 0, 1, 2, 3. Okay? So just to kind of show you how that works, I got time. I'm going to go ahead and kind of do my increasing energy, and I'll kind of show you. I told you I was lying the other day, and I'll kind of show you how I was lying. But here, when n is equal to 1, we of course have the 1s subshell with 1 box. I'm not going to put the boxes. That's okay with you. When n is equal to 2, we have a 2s and a 2p. When n is equal to 3, we have a 3s, 3p, 3d. When n is equal to 4, we have a 4s, 4p, 4d, and 4f. So just for kicks, we can actually, next to each one of these, come up with an n plus L value. And so this is how it works. Like down here, for 1s, guess what? N is 1, L is 0. So the n plus L value is 1. Let's kind of jump to 3p. N is 3, and what's the L value for p? 1. So the n plus L value for the 3p subshell is 4. Now let's get exciting up here, 4d. So n is equal to 4, and what's the L value for a d-type subshell? 2. Okay, so that's how that goes. And what we're going to see is that we could go ahead and come up with n plus L values for all of these. What we're going to see is that electrons go in the lowest n plus L value possible, and then when it's full, that subshell is full, they go in the next subshell. When that subshell is full, if they still need homes for electrons, they keep going up. Okay. That kind of building up is called the Aufbau method. Okay. One thing about it is I kind of say this building up method. It is so cool. And again, if you've kind of done electron configurations, you know this. But let's say we know how the electrons are configured. Let's go 1 less than xenon. You guys would tell me 53 electrons around a neutral iodine atom. Well, for xenon, all you got to do is ding, add 1 more electron. So it's building up. So for instance, if you have cobalt, you're an electron away from knowing nickel. Okay, so that's kind of the building up part of it. And this says, I guess this is pretty important, the second bullet here. If you have subshells that have the same n plus L value, so let's see, an example is these two guys. So if I take 2p, the n plus L value is 2 plus 1 is 3. If I do that for 3s, you would tell me n is equal to 3, L is equal to 0. These are both 3's, right? And what this is saying is that actually, and it's as I've drawn it here with increasing energy, the one with the lower n, even though it has the same n plus L value, the lower n is going to be lower energy. I have something coming up called the arrow diagram, which I really like the arrow diagram. And it helps kind of know what, it applies this n plus L rule. So the Aufbau method is German for building up. Okay. So here's a figure from OpenStax to kind of show you, again, you see the energy, increasing energy over here with the y-axis, and you can kind of see, I suppose it's even kind of showing location. If you put the nucleus over here, we're getting farther from the nucleus, and we are increasing energy as you go up like this. But already, can you see where right up here, this is my little lie in my, right here, and I'll fix this. So notice that if we go up to 3D, let's see, all right, yeah. Actually, you're gonna see this with the arrow diagram, 4s is a lower energy than 3D. It is. They have the same n plus L value, but 4s is a lower energy. This is just a different way to kind of look at what we've got going on here. I like what your author's done. Notice we talked before about the whole, an S-type. An S-type has one orbital. You can fit 2 electrons in any orbital. Thus, you max out with 2 electrons. The p-type, you can see these 3 dashes representing the 3 orbitals in p-type subshells. You completely fill that up, and you got 6 electrons. Okay? D-type has 5 boxes. 5 times 2 is 10. F, okay, 14. Okay, so there's 2 ways to say how the electrons are hanging out, how electrons are configured. I call this the hand cramp method, the box and arrow. Box and arrow notation, and it's kind of what we've been talking about, that the arrows represent electrons. We talked about that m sub s value is a plus 1/2 or minus 1/2. If it's going up, that's plus 1/2, going down, minus 1/2. Okay? Usually, and unless you want to be a rebel and you can, I'm fine, I catch you on the other side. But usually, if there's only 1 electron in a box, we usually show it facing up with a plus 1. But it wouldn't have to. Box and arrow notation is this where you guys have some little boxes to fill in. So how many electrons associated with the hydrogen atom? Just 1. So dun dun dun. There you go. There's the box and arrow notation for hydrogen. So what do we have to do with that second arrow for helium? Point it down. Yep, that's it. And all these are just by increasing atomic number, so increasing number of electrons. So lithium's atomic number 3, so the first 2 electrons go there, and we completely fill the 1s, and then the third one goes in the 2s. And it has an up arrow. Beryllium's atomic number 4, so 4 electrons, 1, 2, 3, 4. Boron's atomic number 5, so the 5 electrons go 1, 2, 3, 4, and 2s, and then 5. We get to start 2p subshell. So that's 5 electrons. Carbon's atomic number 6. Now, in this case, I'm going to show you what that last electron does. It does this. This is what I call kind of the spread out rule. And there's a better name for it. It's actually oftentimes a vocabulary. It's on the next slide called the Hund's rule. This is the Hund's rule in action. And I liken it kind of like if you have a house with 2 children and you have 3 bedrooms you can spare for them, you're going to let them spread out. That's it. Notice that if you do let them spread out, or this is the way that quantum mechanics work, assigning quantum numbers, they will have the same spin. So I said a minute ago, if you want to be a rebel, you can go ahead and make it a -1/2, but then actually the one in the room next to it would also be 1/2. We use the word, and I told you it's a kind of a common vocabulary word, the word degenerate orbitals, because remember, that's what we're talking about. When they're spread out in different rooms, these are the 3 degenerate orbitals of 2p. So that's what I said, Hund's rule in action. It's the spread out rule. Notice that if possible, they will spread out in degenerate orbitals in the same subshell, and the electrons will have the same spin. Now, as I've drawn it here, we call these unpaired. Does it seem unpaired to you? These guys are unpaired. They don't have a roommate. So unpaired electrons are ones that don't have a roommate. So let's go after carbon. We have nitrogen. Oh, sorry. So unpaired electrons were what I showed you with carbon, single electron and orbital. If you go ahead and have 2 electrons of opposite spins in the same orbital, those are called paired electrons. All right, on to nitrogen, 7 electrons. First 2 go in the 1s, the next 2 go in the 2s. And usually I kind of write it out like this. So 7 electrons, I need 3 more. So I go 1, 2, 3, Hund's rule. Then 8 electrons, oxygen atomic number 8, first 2 in 1s, the second 2 in the 2s, and I would usually go, so I need 4 more, so I would go 1, 2, 3. I'd go ahead and spread them out, and then it's kind of, again, like your family's growing, they have to have a roommate. So then I'm going to take that last electron, I'm going to go back to the first orbital, it could be any orbital actually, in the 2p, and I'm going to make them buddy up. So can you see where we just keep building? So we're going to have 1 more electron with fluorine, the first 2 in the 1s, the next 2 in the 2s. And then we're going to go, let's see, looks like we need 5 more. So 1, 2, 3, and then buddy up, suck it up, buddy up, suck it up. Your family's really growing. You have to find homes for 1 more kid, okay, with neon. So 10 electrons look like this. The first 2 in the 1s, the next 2 in the 2s. And then we need to find homes for, that's 4, and we're on our way to 10. So 10 minus 4 is 6. So it goes like this. 1, 2, 3, 4, 5, 6. So as much as I'm kind of making fun of this or making light of this, on your test, your next unit exam, you're going to need to be able to show how electrons are configured using this box and arrow notation. So a few things about this box and arrow notation is notice that I go ahead and make sure that I clearly say what subshell they are underneath the boxes. Okay. The other thing is, get to an example of it. So for instance, for carbon, notice that even though I didn't use that last orbital in the 2p, I put it there. Because you wouldn't want to put 2p and just put 2 orbitals with the electrons. You need to show the 3rd empty orbital. Okay. Well, neon, group 8a, what do we call group 8a elements? Noble gases or rare gases. Yep, noble gases. Rare gases, inert gases, exactly. And as we talk more about them in this unit, we're going to actually see where atoms try to pick up electrons, the nonmetals try to pick up electrons to get, now their hearts would be the same, their nuclei would be the same, but now the electrons they have around the nucleus would be more. So actually like chlorine picks up 1 electron to be like argon, oxygen picks up 2 electrons to be like neon, it gets the heart of an oxygen atom, but it's got the electron configuration or the electrons of a neon atom. In doing so, they become negatively charged. But this is actually an important configuration. We call this, it's probably coming up on a slide here, we call this configuration NS2, because it could be any N, NP6. Oh, where actually the 2 means the 2 electrons in the highest N. These 2 electrons. This is the NS2, and this is the NP6. So yep, that's your rare gas or inert gas or noble gas configuration. Here's a figure from OpenStax kind of showing you hydrogen atom. You told me atomic number 1. It has only, if it's got one proton, it's atomic number 1. So to be neutral, it has 1 electron. So what we do to show the 1 electron like that is we simply take the subshell and we put a superscript 1 there. That 1 means 1 electron. So these 2 things mean the same thing. They mean the same. So that brings us to kind of our so if the box and arrow notation is hand cramp notation, spectroscopic notation is where you go, oh yeah, that's much better. My boxes get really ugly. Okay. So the spectroscopic notation says the subshell, and then it's the superscript, the number of electrons. So these actually should match up with our box and arrow notations. For helium, there were 2 electrons in the 1s, so it's 1s superscript 2. And you'll hear me say 1s, and then I'll pause. The next number that comes after the subshell is the number of electrons there. Lithium, we're done with the 1s. So lithium has 2 electrons in the 1s, so it's 1s2. And it has 1 electron in the next subshell, 2s1. So with spectroscopic notation, you don't have arrows representing electrons, but if you want to know how many electrons you've accommodated or found homes for, you just need to take the superscripts and add them up. So 2 plus 1 is 3. So yeah, we're at atomic number 3, which is lithium. We have room for 1 more electron for beryllium in that 1s, so sorry, in the 2s. So it goes 1s2, 2s2. It's like I'm playing bingo sometimes when I get to this part. So now we're done. We can't put any more in the 2s. We need to go on to the 2p. So for boron, it goes 1s2, 2s2, 2p1. And again, you add up the superscript, so you're like, oh, great, I know I'm at atomic number 5, or I have 5 electrons around the neutral boron atom. Then we go on to carbon, 1s2, 2s2, 2p2. Now, do you see where you lose a little bit of information with this notation of how the electrons are configured versus box and arrow? Because we can't really show Hund's rule here, but we just got to know that in that 2p, I'm going to have 3 boxes, and they're going to spread out. Those 2 electrons are going to spread out to different levels. All right, nitrogen, 1s2, 2s2, 2p3. Oxygen, 1s2, 2s2, 2p4. Fluorine, 1s2, 2s2, 2p5. Again, you kind of know where you are. You add up superscripts, so I'm at 9. And then we're on to, at the end of that period, we have neon, which is our rare gas, 1s2, 2s2, 2p6. So you need to be able to say how electrons configured using both of those. So I mentioned the arrow diagram, and I'm going to go ahead and draw the arrow diagram here. For my intro to general chemistry, actually for this subject, when we cover it, they get credit for drawing the arrow diagram on their test. But for you guys, I don't make you draw it. It's just nice if you do, because it can help you work the problems. So it goes like this. You're basically, instead of having low energy here and high energy there, that kind of goes out the door. Instead, it looks something like this, where when n is equal to 1, we know we have one type of subshell. I'm going to put 1s in that one row. So feel free to draw along if you want. And then we're going to go N is equal to 2, and we have 2 types of subshells. So I'm going to line up my S's and my P's and my D's and my F's. So I have a 2S here, and I'm going to start a new column, 2P. Now, part of the trick in drawing the arrow diagram is to make sure that you get your columns and your rows squared away. When N is equal to 3, I have a 3S, 3P, and I have a 3D. When N is equal to 4, 4S, 4P, 4D, 4F. I'm going to stop with F's, even though we know when N is equal to 5, I have a G, and then we have an H and an I. And we're going to go all the way to 7. So then it goes 5S, 5P, 5D, 5F, 6S, 6P, 6D, 6F, 7S, 7P, 7D, 7F. Now for an arrow diagram, they're just subshells. There's no arrows yet, but here come the arrows. So the arrows are diagonal. That's why if you didn't kind of make your columns right, it gets wonky. So the first arrow goes up here, and it goes through just one subshell. The arrows are directional, like arrows are. The second arrow only picks up one subshell too. That's my second arrow. Now finally, things get exciting with my third diagonal. I get to pick up 2 subshells. In a minute, I'll kind of tell you, well, I'll tell you right now what this is. Each arrow actually, if you do the math like we did over here, each arrow, the subshells they go through have the same N plus L value. For instance, 1S, you would tell me, has an N plus L value of 1. 2S is 2. I'm putting 3 here for both the 2P and the 3S. Okay. Now the other thing, to use the arrow diagram, you start at the top of the arrow and then you go through the entire possibilities of N plus L before you go on to your next diagonal. So the fourth diagonal only has 2 subshells. That's N plus L value of 4. The next one, it gets exciting. We get to pick up 3 subshells, N plus L value of 5. The next diagonal, again, 3 subshells, N plus L value of 6. The next diagonal, oh, see, I feel like I'm getting a little sloppy here, N plus L value of 7. The next diagonal, N plus L value of 8. N plus L value of 9. And what do you think? 7F, let's see, N is equal to 7 and F is equal to 3. Yeah, that's 10. N plus L value of 10. So this is just a tool to know which subshell to go to next. So I'm going to be referring to this. We're going to do a couple of examples, and then we've got time. I didn't want to get all the way through this part, kind of on purpose. We'll finish this part on Friday, but then I'm going to kind of turn you loose. Your ticket out of here is to do a couple of electron configurations. You can work with your lab partner, whatever. So pay attention. We'll lock the door. Okay. All right. So this is how your textbook does it. Now, I prefer how I do it, even though it's got some miscellaneous stuff that probably doesn't have to be there. I just think it's easier. It's a similar deal, very similar deal. All right. So if we find potassium on the periodic table, we're going to find it has an atomic number of 19, so it has 19 protons. It means we need to find homes for 19 electrons if it's a neutral atom. And notice there's no charge in the upper right-hand corner. So we're gonna go spectroscopic notation, which is better than the box and arrow, I think. So if we're using this, actually I have my builds here. Notice here's the arrow diagram, and we're going to go on the first diagonal. At the top, there's only one subshell on the first diagonal. So that's where we're going to go. And then over here, you can see I've gone ahead. I'm going to write the electron configuration down under here. So our first stop is 2 electrons in the 1s. So it's 1s2. That's our first stop. Sometimes what students do, and I can see why they do it, and it's fine with me, is they actually kind of up here at the top, so these are all S's, these are P's, these are D's, these are F's. Sometimes at the top they'll say you max out at 2 electrons, you max out at 6 electrons, you max out at 10 electrons, and you max out at 14 electrons. Just kind of if you wanted to. So we're far P's from 19. The next 2 electrons are going to go, we're going to go on to the next diagonal. So the next diagonal just has one subshell. It's an S-type also. This is 2s, superscript 2. Okay, I promise not to belabor all of them like this, but I'm just trying to kind of get us used to this. So we've accommodated 4 electrons. If we stop now, we would be like beryllium. So now we're going to go on to the third diagonal, but we're going to go 2p, and if we need more room, we're going to go to 3s. So after the 2s2 becomes 2p, and I'm going to put a superscript 6 because, yeah, I need homes for electrons. I'm not done by any means. I've only met 10 electrons now. I'm on my way to 19. When I do these on a test or an answer key or something, I always write down in parentheses 19. I write down the number of electrons in my target, 19. So this actually then, when we get to the end of the period, of course, that's the group 8A. Those are rare gases. And so I'm going to go ahead and mark those on my electron configuration. You wouldn't have to, but I'll kind of show you why I would want to do that later. Dun, dun, dun. Anytime you have an NP6, you actually check it out and you've arrived at a rare gas. 10 electrons is neon, it's a rare gas. So now we're going to continue on that third diagonal. So now we're going to 3s, and we better go ahead and fill it. So 3s2. Now we're on to the top of the third diagonal, but we go 3p, and do we need all 6 electrons there? Yep. So 3p6. So now if I add them up, one good reason to go ahead and kind of mark your electron configurations with your rare gas is you're like, okay, I'm 10 there, so 10 plus 8 is 18. I'm at 18 now. Wow, so I'm at argon. Right? So let's go ahead and mark it. We're at argon. I only need 1 more electron. I'm almost done. But this is where actually I try to kind of unscramble it. Okay? This is actually according to the rules of electron configuration. 3s is a lower energy than, 4s is a lower energy than 3d. So from 3p, I'm going on to 4s, not 3d. So do I need to go ahead and fill the 4s? Nope, because I only need home for 1 more electron. So that's 4s1. That's it. A good check for, and we'll talk more about other checks on Friday, but a good check is to make sure all your superscripts add up to, in this case, 19. All right. So that was potassium. Let's take it up a few electrons. Said 19, let's go 40. So zirconium, the element is atomic number 40. And so if it's neutral, which is being shown up here, we need to find homes for those 40 electrons. So the first 2 electrons go into 1s, so 1s2. The next 2 electrons go into 2s, so 2s2. The next 6 electrons go into 2p, 2p6. And according to our error diagram, we're on to the 3s. We're completely fill it, 3s, wait. So now that I've come to something p-type orbital with 6 electrons, I am at neon. So we'll go ahead and mark that. Now we're going to go on to 3s, and we'll fill it, 3s2. Then we're going to go on to 3p, and we'll fill it, 3p6. And I've reached another rare gas. Of course, that's argon. So far, this is kind of the same thing as when we went for potassium. This is where it deviates from potassium, because now I am ready for the 4s, and I'm going to go ahead and totally fill it. So it's 4s2. Now I get real excited because now we're on to the next diagonal, starts with 3d. So let's see where we're at. 18 plus 2 is 20. And in a D type, I can accommodate what, 10 electrons? So 20 plus 10 is 30, and I need 40. So I'm going to completely fill that through that 3D, aren't I? So 3D 10. I'm liking it. So what did I say? So that brings us to 20, 30. The next place to put things is in a P type, and I would put 6 in there if I need it. So 36, Yep, I'm going to be totally needed, aren't I? So I'm going to totally fill the 4p, 4p6. And again, we must have reached a rare gas. It would be the rare gas in the period be underneath, or the next period beyond argon, that's krypton. So now I am ready to go ahead and go on to the 5s subshell. So 36 plus 2 is 38, and I need 40. So yeah, I'm going to go ahead and make it 5s2. Now I'm ready to go to the 4d subshell. And if I have what did I say, 38 here? Now the D's can take 10, but do I need 10? No. So if I'm on my way to 40, then I only need 2 more. So it's a 4D2, and that's it. I'm going to kind of show you some scrambling or unscrambling. This is the electron configuration. I like these big words. Electron configuration using the spectroscopic notation. And this is in what's called the order of filling. Okay. Now, I think, I'm pretty sure we talked about this idea of valence electrons, the fact that some electrons are actually extra special. They are electrons that are in the highest N. So when I talk about highest N, I mean the N of the subshell. So for instance, we have N is equal to 1, N is equal to 2, N is equal to 3 for both of these. And this one, N is equal to 3, N is equal to 4 for both of these, all 3 of these. And we have N is equal to 5 right there. So actually, our highest N is equal to 5. And so the valence electrons, there are 2 of them, and they are the 5s2 electrons. So sometimes it's nice to rearrange this from order of filling to the order of increasing N. So this right here is exactly what you had on the bottom of the previous slide. If I go ahead and unscramble them in the order of increasing N, this is what they look like. Where these are the same electron configurations, they're just, I've taken subshells and I've relocated subshells in their order. So this actually emphasizes that 5s is the highest subshell with electrons. There are 2 there. So those would be our valence electrons. Okay, so we did 40 before. We started with, what, 19, went to 40, let's do 53. What the heck? So iodine, you find it on the periodic table, and it's clear over here. And so we need to find homes for those 53 electrons. Actually, I can kind of zoom through it a little bit because iodine and zirconium, which we just did, are in the same period. See, we just did this one. Okay, so we could actually kind of rewrite what we wrote and just kind of build up to. So in the order of filling, it goes 1s2, and then 2s2, 2p6, and of course we've reached argon. Oh, sorry, neon, direct. Argon's coming up. We've reached the rare gas neon. Beyond that, we have a 3s2, 3p6, and now we've reached argon. Then after that, using the arrow diagram, we're going to go to 4s2. Using the arrow diagram, we go next to the top of this diagonal, so we go 3d10. And then 4p6. I must have reached a rare gas, that being krypton. According to the arrow diagram, we go on to 5s. And notice that I'm with krypton, and 5s would bring me to what? Strontium. So 5s2. Now I'm going to go ahead and, this is actually, I'm kind of getting ahead of myself to next, what we're going to talk about Friday. But if you count these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. 10 elements there. And actually, as I am populating the 4D subshell, I am adding electrons for each one of these. So it's kind of, and again, we'll talk about this on Friday, but you can actually kind of use the periodic table as your guide. So now I am up to cadmium, eye on the prize, okay? 1, 2, 3, 4, 5. So I'm 5 electrons away. According to my arrow diagram, I'm going to go to the 5p, and I'm not going to fill it. I'm going to go 5p5. So if we assume this is right, which it is, I have 36 electrons to there. 36 plus 2 is 38. 38 plus 10 is 48. 48 plus 5 is 53. Okay, so yeah, we're at 53 electrons. That's totally terrific. So I use a combination of the arrow diagram and kind of the periodic table a little bit sometimes. Okay, so the green says in order of filling. If we want to unscramble them, which you're going to see here in a minute, but do you see, even if we didn't unscramble them, hopefully you would tell me the highest N is subshells that have a value of 5, and I have 2 electrons in the 5s, and I have 5 electrons in the 5p, so I'm counting 7 electrons. 7 valence electrons, and that is totally right. So that's the order of filling. If we unscramble it, it looks like this. Sometimes students say, well, Mrs. Snipes, on a test, if I'm showing you how electrons are configured, can I just use the arrow diagram or whatever, show you the order of filling? Do I have to unscramble it? And the answer is you do not have to unscramble it. So students like this. I'm kind of smiling because I like this. Remember how we kind of did those milestones? Anytime you have an NS2, NP6, those are rare gases. But there are certain rules to using this abbreviated rare gas notation. You have to use the last rare gas you just passed. And for us, for iodine, the last rare gas we passed was krypton. So what you're going to see is we're going to put krypton in brackets, and then everything past krypton needs to be shown here. So it looks like this. Now, this actually was kind of unscrambled. You might have given me bracket Kr, which meant 36 electrons, and then you might have gone 5s2, 4d10, 5p5, which is probably what I would have done. Just kind of looking at this unscrambled one up here. Right there was our break. So these 3 subshells are these 3 subshells right here. Okay. So anyway, yeah, that's kind of nice. So rules for using the abbreviated rare gas form. You have to use the rare gas that was in the period directly before the element of interest. You can't just pick which one you want. Okay. You need to go ahead and use brackets, square brackets. And that will be what we call your kind of core. And it says this form can be used with box and arrow notations. I don't think so. Okay, so I mentioned this. I'll give you a few minutes and part of your ticket out of here. You can work together if you want. I have 2 elements and the 2 types of ways to show how electrons are configured. So I want you to find chlorine, and you probably need a periodic table. I would. I want you for chlorine to go ahead and say how the 17 electrons are arranged using the box and arrow notation. And don't use the abbreviated rare gas notation. I want to see the whole thing. And these are things, actually, you can tear it out if you want to, but you're just going to show them to me and you don't have to turn anything in. So you're just going to show them to me, and again, you can work together. So do those 17 electrons for chlorine, and then do iridium, which I picked it on purpose. Okay, so iridium, actually, I'm going to warn you, is going to drag you through F electrons too. So 77 electrons around iridium. Spectroscopic notation, not box and arrow. And then you can use abbreviated rare gas notation, but I would avoid it right now still. But definitely use your arrow diagram. Once you're done with that, you're free to go. Well, you show me. And again, you can work together or compare answers. Can't do it on tomorrow's test, but